Today we can see the term Poisson's ratio and the various elastic constants. You are familiar with the term Poisson's ratio that you have already studied it in your plus 2 classes. From this figure itself, I can define Poisson's ratio. This is an experimental setup for a compression testing machine. Compression testing. In this, a bar is tested under compression, and by the application of this compressive load, the length of that bar get reduced, whereas the diameter of the bar get increased. That is, by applying a compressive force, lateral dimension get increased, whereas the longitudinal dimension get decreased. Then the ratio, there will be strains in both directions, both in lateral as well as longitudinal direction, and the ratio of strains of these two, that is lateral strain to the longitudinal strain, is termed as Poisson's ratio. Here, in this first figure, you can see a cylinder of diameter d, and it is subjected to a tensile force F here, and by this application of the tensile force, the length of the cylinder gets increased from L to L plus delta L, whereas the diameter of the cylinder gets decreased from d to d minus delta d. So the longitudinal strain, that is change in length of the member divided by original length, that is equal to delta L by L. Then there is a strain in the lateral direction also. The change in diameter is d minus delta d. That is change in diameter is delta d, and the ratio of that to original diameter, that will give the lateral strain. Then ratio of lateral strain to longitudinal strain is termed as the Poisson's ratio. Next, we can consider the case of a rectangular section of depth B and width C. And this is subjected to a tensile force P here. And by the application of this lateral force, the length of the member gets changed from L to L plus delta L, and the width get reduced. And that is, other two lateral dimensions get reduced. And the longitudinal strain, that is the ratio of change in length to original length, that is equal to delta L by L. Whereas the lateral strain is a change in dimension in the lateral direction to that of the original dimension, that is delta B by B as well as delta C by C, that represent the lateral strain. The ratio of lateral strain to longitudinal strain, that is the Poisson's ratio. And for most of the metals, the Poisson's ratio ranges between 0.25 to 0.33, whereas for steel it is 0.3, and for concrete it is 0.15. For civil engineers, the Poisson's ratio of these two are important because for many of the structures we may have to use either steel, or we may have to make use of concrete as well as steel. Now comes volumetric strain. When a member is subjected to stresses, it undergoes deformation in all the directions. Then, as the name indicates, the volumetric strain, it is the ratio of change in volume to the original volume. That is, volumetric strain is given by delta V by V, where delta V is the change in volume and V is the original volume. Then, in order to represent the volumetric strain in terms of lateral as well as longitudinal strains, we can consider a bar of length L, width B and depth D, and the length and the volume of this bar, that is equal to the L into B into D. And the volumetric strain is given by change in volume to the ratio of change in volume to the original volume. So that we have to find out the change in volume. Then the volume, it is a function of length, breadth as well as D. So the change in volume includes the changes in length, changes in breadth as well as changes in depth. So delta V, it can be represented as delta L into BD plus L into delta B into D plus LB into delta D, which includes the changes in length, width as well as depth. Then we can find out volumetric strain EV, which is equal to delta V by V or delta V divided by LBD, which is the initial volume of the bar. So EV is equal to, we can divide delta V, that is equation number 2, divided by equation number 1. That will give volumetric strain is equal to delta L by L plus delta V by V plus delta D by D. Here L is the length of the bar, B is the width of the bar, and D is the depth of the bar. So the first ratio delta L by L, that is the change in length to original length, that is the longitudinal strain represented by Ex. And delta V by V as well as delta D by D, they are the lateral strains, that is the changes in lateral direction divided by the dimension in that direction. So delta B by B, that is EY, and delta D by D, that is EZ. Here the dimension in Y direction, it is B, and dimension in Z direction is D, which is the depth of the bar. So the volumetric strain is sum of Ex, Ey, and Ez, that is sum of longitudinal strain as well as the lateral strains in other two directions. Thus volumetric strain is the sum of strains in three mutually perpendicular directions. Now we can consider the case of a circular rod of length L and diameter D. Here also we can find out the expression for the volumetric strain. Then volumetric strain is change in volume by original volume. Then initial volume of the bar is cross-sectional area into length. So it is pi by 4 d square into L. L is the length of the bar. And here volume, it is a function of diameter as well as length. So the changes in volume includes the changes in diameter, that is delta D, and change in length, that is delta L. So we can differentiate that with respect to D as well as L. Then so the first term pi by 4 differentiating with respect to D, pi by 4 into 2D delta D into L, plus second term, that is differentiating with respect to L, pi by 4 d square into delta L. Now the volumetric strain EV, which is equal to delta V by V, that is dividing this with a pi by 4 d square L, that will give 2 into delta D by D plus delta L by L. In this delta L by L, that is the change in length divided by original length, that is equal to the longitudinal strain represented by Ex. Then the directions here in Y as well as Z directions, then the dimension of the cylinder, it is D itself. So Ey as well as Ez both are given by delta D by D. So 2 into delta D by D, that is can be written as Ey as well as Ez. So the strain, which is the volumetric strain, that is the sum of strains in three mutually perpendicular directions, which is true for the circular rule also. Now we can see the next elastic constant. We have already seen the two elastic constants, modulus of elasticity or Young's modulus, then comes modulus of rigidity or shear modulus. Here is the third elastic constant, which is the bulk modulus. That is the ratio of uniform pressure applied in three mutually perpendicular directions to the volumetric strain. Here, when a body is subjected to identical pressure P acting in three mutually perpendicular directions, then the body undergo uniform changes in three directions without undergoing distortion of shape. That is, the shear deformation is not taken into account. Then the ratio of change in volume to the original volume, that is the volumetric strain, and the ratio of uniform pressure to the volumetric strain, that is the bulk modulus. That is K is equal to P by EV, and EV is a volumetric strain, which is delta V by V, and P, that is the identical pressure applied in three mutually perpendicular directions. Thus bulk modulus can be defined as the ratio of identical pressure P acting in three mutually perpendicular directions to the corresponding volumetric strain. Now we can derive the relationship between the three elastic constants. First, we can derive the relationship between modulus of elasticity and bulk modulus. For that, here we are considering a square element and it is subject to stress P in three mutually perpendicular directions. You can see the stress P, that is the tensile stress P, acting in three mutually perpendicular directions. Then, this tensile stress P that will cause tensile strain P by E in x direction. And because of this tensile stress P, then strains in the lateral directions will be compressive and that strain, lateral strain is given by mu into P bar A because we have already studied that the Poisson's ratio mu is equal to lateral strain divided by longitudinal strain. And the longitudinal strain is equal to P by E and mu into P by E, that is the lateral strain. And because of the P in x direction, we have the tensile strain P by E in x direction, and due to this P in y and z directions, we have the compressive strain mu into P by E in x direction. So the total strain in x direction is P by E minus mu into P by E due to the stress in y direction, mu into P by E due to the stress in z direction. We can write it as P by E into 1 minus 2 mu. In the same manner, we can consider the total strain in y direction. Because of the tensile stress P in y direction, we have the tensile strain P by E in y direction. And due to the stresses P in x and z directions, which are tensile in nature, we have compressive strain mu into P by E in y direction. This is due to the stress in x direction as well as due to the stress in z direction. So we can write it as P by E into 1 minus 2 mu. Then same is the case for the strain in z direction also. So the total strain, which is the sum of the strains in three mutually perpendicular directions, that is EV is equal to Ex plus Ey plus Ez. We can add these three to get the volumetric strain, which is 3P by E into 1 minus 2 mu. Then here we are going to define the relationship between modulus of elasticity and bulk modulus. Earlier we have seen that the bulk modulus is given by pressure divided by the volumetric strain. Here we can substitute for the volumetric strain as 3P into 1 minus 2 mu by E, and from this we will get E is equal to 3K into 1 minus 2 mu, which gives the relation between modulus of elasticity E and bulk modulus K. Here mu is a Poisson's ratio. Next we can derive the relationship between modulus of elasticity and modulus of rigidity. When the term modulus of rigidity comes, you should think about the shear stress, shear strain, all these things. So we are considering a square element of side A and it is subjected to pure shear Q. Here it is subjected to pure shear Q. So one set of shear will be accompanied by another set of shear of same intensity in the case of pure shear. Now for the element, the initial shape is A, B, C, D, and due to this shear stress Q, the deformed shape is represented by A, E, C dash and D. There is certain shear deformation which is represented by phi here. Shear deformation is phi. Now let us draw a perpendicular to DE at F. That is BF is perpendicular to DE. BF is perpendicular to DE. Now, let us write the expression for strain in diagonal BD. The strain is given by the change in length divided by the original length. BD. We have to find out the strain in this diagonal. So here we are dropping a perpendicular at point A, that is BF is perpendicular to DE. So the length DB from this figure, length DB, that is equal to DF. And strain in the member DE is equal to DE minus DF, which is equal to DB itself, that divided by DB, that is again is equal to DF. So the strain is given by EF by DB. Then DB, it is a diagonal of the square of side A, which is given by A root 2. For a diagonal having side A, so for a square having side A, the diagonal is given by side into root 2 or AB root 2. It is written here. Now we can write this in terms of shear deformation phi. Then here the angle of, in the case of shear strain, we are considering that the angle of deformation is very small. If phi is very small, then we can assume that this is 45 degree itself. Since this angular deformation is very small, this angle is taken as 45 degree itself. So this angle is also 45 degree. Then we can write EF is equal to BE cos 45. Now strain in diagonal BD, that is given by EF divided by BD. Here it is written that EF divided by BD. Instead of EF, we can substitute it as BE cos 45 that we have obtained here. BE cos 45 divided by BD, that is equal to A root 2. And from this figure, this angle is phi. Then we can write tan phi is equal to, which is opposite side by adjacent side, tan phi is equal to BE divided by AB, or BE is equal to AB tan phi, and we know that AB is the side of the square, or A tan phi. You can substitute it here. A tan phi cos 45 by A root 2. And cos 45 is 1 by root 2. So this becomes 1 by 2. A will get cancelled, and 1 by 2 tan phi. Since the value of phi is very small, tan phi is equal to phi itself. Here phi is the shear strain, and the relation between the shear stress and shear strain, that is modulus of rigidity G, is given by shear stress. Here it is used by the notation Q divided by phi, that is modulus of rigidity is given by shear stress by shear strain. So we can substitute for phi as Q by G. So the strain in diagonal BD, that is given by 1 by 2 into Q by G. Now the pure shear gave rise to axial stress along the diagonals that we have studied in the previous classes. That is, in the case of, I shall draw it here, and for this condition, for diagonal BD, we will have the tensile strain, whereas in diagonal AC, we will have the compressive stress, and both are of same intensity, and both will have the same intensity Q. This will be tensile, and whereas this will be compressive. Due to the tensile stress Q on diagonal BD, the strain in diagonal BD will be Q by A, and because of this compressive stress Q in diagonal AC, the strain in diagonal BD is equal to minus mu into Q by A. So this will give rise to Q by A plus mu into Q by E. Mu is the Poisson's ratio. That is written here. So the tensile stress along the diagonal BD is Q by E into 1 plus mu. We have already got the expression for the tensile stress along diagonal BD, which is 1 by 2 into Q by G. Equating these two, we will obtain the relation between modulus of elasticity E and modulus of rigidity G. And the relation is E is equal to 2G into 1 plus mu. This is the modulus of elasticity, G is modulus of rigidity, and mu is the Poisson's ratio. Now we can derive the relation between the three elastic constants, modulus of elasticity, modulus of rigidity, and bulk modulus. We have the two relations so far. Modulus of elasticity is given by E is equal to 2G into 1 plus mu. G is the modulus of rigidity. E is equal to 3K into 1 minus 2 mu. K is the bulk modulus and mu is the Poisson's ratio. And from the first relation, we can eliminate mu, or we can write mu as a E divided by 2G minus 1. And we can substitute the expression for mu in the second expression for E. That is, E is equal to 3K into 1 minus 2 mu. Instead of mu, we can substitute E by 2G minus 1. And simplifying the terms, we will obtain E is equal to 9kg divided by G plus 3K. And this can also be written in other forms, that is 9 by E is equal to G plus 3K divided by Kg, or 9 by E is equal to 3 by G plus 1 by K. This gives the relation between the three elastic constants, modulus of elasticity E, modulus of rigidity G, and the bulk modulus K. Then I shall explain these two things once again. That is the two-dimensional stress-strain relation. Then if sigma 1 represent this, we have make use of in the derivations of the relations. Then if sigma 1 is the normal stress in x direction and sigma 2 is the normal stress in y direction, and E1 is the total strain in x direction and E2 is the total strain in y direction. Here I can consider one at a time. I am here the element A, B, C, D, and it is if it is subjected to sigma 1 alone, then because of this tensile stress, this may be the deformed shape, and I can write the expressions for Ex and Ey here. Ex, Ey, and because of the tensile stress sigma 1 in x direction, the tensile strain in x direction, that is Ex, will be sigma 1 by E. And due to this tensile stress sigma 1 in x direction, the strain which is compressive in y direction, that will be minus mu into sigma 1 by E. Now I can say as a second case, I can consider this. As a second case, I can consider the effect of sigma 2 alone, sigma 2, which is again tensile, that is acting in y direction. And here, because of this tensile stress, this will be the deformed shape. And the strain in y direction due to sigma 2 will be sigma 2 by E, which is tensile, and strain in x direction due to sigma 2, that will be compressive in nature, and magnitude is mu minus mu into sigma 2 by E. So the total strain in x direction is sigma 1 by E minus mu into sigma 2 by E, and total strain in y direction, which is represented here as E2, that is sigma 2 by E minus mu into sigma 1 by E. We can extend this for the three-dimensional case also. Here sigma 1 represents the normal stress in x direction, sigma 2 normal stress in y direction, sigma 3 normal stress in Z direction, E1, E2, E3 that strains in X, total strain in X, Y and Z directions. And E1 is given by sigma 1 by E minus mu into sigma 2 by E minus mu into sigma 3 by E. Whereas C2, that the strain in Y direction, it is sigma 2 by E minus mu into sigma 3 by E minus mu into sigma 1 by E. And E3, that is the strain in Z direction, is sigma 3 by E minus mu into sigma 1 by E minus mu into sigma 2 by E. Here in this class you have seen the Poisson's ratio and the elastic constant bulk modulus and the relation between modulus of elasticity and bulk modulus, modulus of elasticity and modulus of rigidity. Then the relation connecting all the three elastic constants, the relation between modulus of elasticity, modulus of rigidity as well as bulk modulus. Okay, thank you.